Okay, now let's start with a new chapter, ideal gases. Now, in the first place, what is an ideal gas? Your past years will generally tend to ask you to define what is meant by ideal gas, whose mark will usually be 2 marks or 3 marks. So the full complete definition of an ideal gas is generally, it is a gas which obeys the equation PV over T equals to constant for all values of P, V, and T, where P is pressure, V is volume, and T is thermodynamic temperature. This one definition can be used for 3-mark question. Okay, so this is the full definition of it. All right, so PV over T being a constant is known as the general gas law, which tends to give you this one. P1 V1 over T1 is equals to P2 V2 over T2. Now, when you're talking about an ideal gas, you can make a real gas behave like an ideal gas by changing 2 parameters of the gas, by making sure that the gas is at very high temperature and at very low pressure. This one will make your gas behave like an ideal gas. And one thing to note is that when you're trying to use the general gas equation, the general gas law equation, your temperature T here must be in kelvins, okay, right? Now, when it comes to gases also, you also can measure gas in a different way in terms of number of moles, okay? We don't measure in terms of kg, we don't measure in terms of meter cube, we don't measure the mass, we don't measure the volume. Instead, we measure it as amount of substance, which is number of moles, all right? So 1 mole is defined as the amount of substance that contains 6.02 times 10 power 23 number of particles, atoms, or molecules. Okay, this is again a definition question. This is actually a unit definition. Okay, physical quantity is amount of substance. Unit is mole. Okay, that's what we are talking about right now. Amount of substance is your physical quantity itself, but the unit of amount of substance is mole. Okay, so 1 mole is actually this definition. That 1 mole of something would have this many particles inside. It can be an atom, it can be a molecule. All right. Sometimes in the marking scheme, you might see that 1 mole is defined differently, where they tell you it's the amount of substance that contains the same number of particles as there are atoms in 12 grams of carbon-12. Now, 12 grams of carbon-12 has these many particles also. These many atoms now, all right? So that's why we can say 1 mole is the amount of substance that contains the same number of particles as there are atoms in 12 grams of carbon-12. It's actually meaning the same thing, okay? Now, there's also something called Avogadro constant, which you need to know. Avogadro constant, you know the number is 6.02 times 10 power 23. You can define it as just the number of atoms contained in 12 grams of carbon-12. Okay, this is the definition of your constant, which sometimes your sometimes your exam paper will also ask. Define what is the Avogadro constant. What is meant by the Avogadro constant? All right. Okay, then we go to ideal gas equations that you need to know. This one, general gas law, is one equation that you will use, but there are some other more specific ideal gas equations that you will use. All right. Now, in general, when it comes to ideal gases, maybe I should just zoom in, sorry. Maybe I should zoom in and do like this. Okay, yeah, this is better. All right. Now, in general, when it comes to ideal gases, for any given mole n of gases, your constant PV over T constant equals to PV over T equals to constant will always be a multiple of the number of moles, regardless of the PV and T of the gas used. Okay, what do I mean by that? It's something like this. Say, for example, you have 1 mole of gas, all right? and then that gas, you did something to the gas by heating it up or increasing its pressure, such that in say one particular case, you have P1, V1, T1. And then another case, you have P2, V2, T2. And then another case, you have P3, V3, T3. Now here, this one is you do for 1 mole only. And then you go and did something to the gas by changing the pressure, the volume, the temperature. So what they found was that no matter what you do to that gas, the PV over T would always be equal to some sort of constant. It will be, in your case, 1 times of R. Okay. Meaning to say this one will be P1, V1 over T1, P2, V2 over T2 equals to P3, V3 over T3. No matter what you do to the gas, it will just be equals to 1R. Okay. Then if let's say you did the same thing to the gas, but this time I tell you that the gas is a different number of moles. Say maybe you use 2 moles of gas, and then you go and change it to different states, where again you say for state 1 you have P1, V1, T1, state 2 you have P2, V2, T2, and then state 3 you have P3, V3, and T3. What they also say is that the ratio of PV over T, regardless of which state you're talking about, would just be 2R. Okay, which means that P1, V1 over T1 is equals to P2, V2 over T2 equals to P3, V3 over T3, which is equals to 2R. Okay, so you do the same thing for different number of moles. If you did it for 2 moles right now, you can repeat the process for say 3 moles, and then after that 4.5 moles. You eventually find out that no matter what values of PV and T that you have, PV over T will be equals to 3R for 3 moles. PV over T for 4.5 moles will be 4.5R. Okay, so it's from this that you can actually get some sort of conclusion that for any net number of moles of gas, for n moles of gas, PV over T is actually NR. So you rearrange this, this is actually PV equals to nRT. Now, this is the equation that you guys would have been using quite a lot from SPM, IGCSE, even up to A levels now when it comes to ideal gas, right? So this is the equation that you all should know by now, where R is the universal molar gas constant worth 8.31 joules per mole per Kelvin. This one you can get from the data sheet, all right? If you don't remember the value, it's fine. You can get it from your data sheet on the second page of your exam paper, all right? Now, you just really need to remember this equation. How it came about, which is explained right over here, you don't need to know, okay? So don't need to bother about that. You just need to know that you have PV equals to nRT. And then from PV equals to nRT, you can actually go and manipulate it a little to give you another separate equation. Now, number of moles is actually number of gas molecules divided by your Avogadro constant. It is something that you also learned in chemistry at some point. Okay, number of moles is number of gas molecules divided by your Avogadro constant. All right, where we can now say N is big N over Na. Now, if you look at the equation PV equals to nRT, if I sub in for small n, the number of moles, I'm going to get big N over Na. So my equation now becomes something like this. All right. Now I go and rearrange it further again. I want to group R and Na together so that now I get PV equals to N R over Na times T. Now this R over Na, you notice that R is a constant in the first place. The Avogadro constant is also a constant in the first place. So a constant over a constant will give you a new constant. Okay. R is a constant, Avogadro number is a constant. So the ratio of the two constants gives you a new constant actually, which is actually your Boltzmann constant. Okay, K. All right, which is defined as molar gas constant divided by your Avogadro number, giving you this value. Again, which you can also get from your data sheet in page 2 of your exam paper. All right, so your equation PV equals to nRT before here can actually be rewritten as PV equals to NKT. Okay, but bear in mind that there are some things that are different really. This N here refers to number of moles. This big N here refers to number of molecules. Okay, right? Yeah. Hi, Angie. We just started ideal gases. We are under page 1. All right. Okay, right. Yeah, no worries, no worries. Okay, the lesson is recorded. Okay, now let's move on to page 2. All right, now page 2, we now need to talk about something called kinetic theory of gases, which again you may have learned. Now, in the previous chapter, thermal properties of material, we actually kind of mentioned something about kinetic theory of matter, right? Where we say that any matter, regardless of whether the solid, liquid, or gases, consists of many small particles called atoms that are always moving, right? So that same kinetic theory of matter is applied to kinetic theory of gases. Okay, it's actually talking about the same thing, all right, just that we are applying for gas right now. So one of the assumptions, basic assumptions of kinetic theory of gases is generally this: your gas consists of many particles called molecules. The total number of molecules is very large. These molecules are always in constant random motion and obeys Newton's law of motion. And then whatever pressure on a container containing the gas is actually the result of the reaction on the walls as the molecules strike and rebound on the walls. Okay, so let's just say, for example, you have a cube looking container like the ones that you're seeing right over here, which contains gas molecules. Your gas molecules are all moving in many random directions. Okay, so as they're moving in random directions, they will eventually hit different parts of your container. All right, so when they hit, say, this side of your container, this wall of your container, it exerts a force onto the wall. So the force acting over a certain area gives you pressure here. Okay, because remember, pressure is force over area. So the collision of the gas molecules with the wall gives you force. You take the force divided by the area, you get pressure. All right, this is how your pressure actually came about from gas molecules. That's why we can say this. Pressure on the container is the result of the reaction of the walls as the molecules strike and rebound. Okay, so that one is okay. Now, basic assumptions of kinetic theory of gases. This one usually they don't really test you as much. These are the basic assumptions which you supposed to have known from IGCSE or SPM. When in the exam, they won't test you on this. Okay, in the exam, they'll actually test you on the more important assumptions of kinetic theory of gases, which is the table below here. Now, this one you really need to remember, okay, because they will ask you what are the important assumptions for kinetic theory of gases. Okay, kinetic theory of gases. This one you need to know because they will ask you to list down the assumptions, okay, for kinetic theory of gases. Now, so the first assumption for kinetic theory of gases is that they will say that the gas molecules have no intermolecular forces. Okay, this is number one. And then number two, they'll tell you that the total volume of gas molecules is negligible compared to the volume occupied by the gas. Okay, so read the statement carefully. The volume of gas molecules is negligible compared to the volume occupied by the gas. Or sometimes it can be replaced with this now. It is negligible compared to the volume of the containing vessel. Okay, So to give you an idea of what we mean by this, is something like what you're seeing right below here. You see, if you're talking about the gas molecules inside this container, you're really only talking about these gas molecules only. Okay, only these molecules. These are your gas molecules here. If you try to add them all up together, the volume probably would just be like this. This is the volume of your gas molecules all added up together. But then when you compare with the volume of your containing vessel or the volume occupied by your gas, the volume occupied by your gas or the volume of your containing vessel is something like this. You see, that's why we will say to you that when you compare the volume of your gas molecules versus the volume of your containing vessel or volume occupied by the gas, volume of gas molecules is actually negligible compared to the volume of containing vessel. Okay, this is the important assumption of kinetic theory of gases. And then the third assumption here that is also important for you to know is that these molecules are always in random motion. Okay, when we say something is moving in random motion, it has something to do with the direction as well as the magnitude of their speeds. Okay, so when we say that molecules are in random directions, moving in random motion, they will move in all possible directions with different speeds. Okay, direction-wise, they will always be different. Magnitude-wise, they'll always be different. That's what we mean by random here. All right. And the fourth assumption of kinetic theory of gases is this, where we say that collisions of the gas molecules with each other in the walls are elastic. Hence, the molecules actually move with uniform velocity before and after collision. Okay. What we mean by that is something like this. If I tell you, for example, this is the wall of your containing vessel, and then after that, you have a gas molecule that moves this way with and is moving towards the wall with velocity v. If it collides with the wall, it will eventually rebound. Okay, but because this one is elastic collision, it will actually rebound with the same velocity v. Okay, meaning to say, if I tell you, for example, this one is 10 meter per second, it will also rebound with 10 meter per second. This is what uniform velocity means. The velocity is the same. Velocity uniform here can also mean constant. Okay, this is actually something that you will learn in dynamics in AS. When you have elastic collision with something, the speed on collision is the same as the speed on rebound. Okay, so it's something similar again here. All right. Okay, so the last assumption or important assumption kinetic theory of gases is this: time of collision is negligible compared to time between collisions. Okay. Now this one you will make use of this fact in your derivation in the next page. Now, when we say time of collision is negligible compared to time between collisions, what is time between collision in the first place? Now, time between collision is the time it takes for a gas molecule to hit the same wall again after rebounding from it. Okay, what we mean by that is something like this. If I tell you that these are the walls of your containing vessel when viewed from, say, the front, your gas molecule hits the wall, it will rebound from it, and it will go all the way here, hitting the wall again, and then after that rebounding back before hitting back the same wall, right? So the time that it took for your gas molecule from rebounding away from the wall, going to the other wall, and then bouncing back to hit back the same wall, this is what we mean by time between collisions. Okay, In other words, it's just the time taken for your gas molecule to hit back the same wall after rebound. That's what this statement is trying to tell you. Okay, so time of collision is negligible compared to time between collisions. Now, time of collision itself could just be this one. I mean, time of collision is this thing here. Wait, let me see what color can I use. When your gas molecule hits the wall, the time that your gas molecule is in contact with the wall, that one is called time of collision. Okay, this one is very, very small. Okay, so when it comes to kinetic theory of gases, we will tell you that one important assumption is that the time of collision of your wall, the time of collision of your gas molecule with your wall is very, very small to the point that it is negligible compared to the time between collisions. Okay, now you make use of this later for a derivation of one particular equation. All right, but just know that this one is one important assumption when it comes to ideal gases. All right, so you have to remember all 5 of these assumptions because you will be asked to reproduce the answers at some point. All right, okay, so this is kinetic theory of gases, and then after that there's one thing that I just want to go. Okay, Brownian motion, I'll just skip it first because this one doesn't really relate to what we're doing right now. Okay, there's this thing here. All right, that we can do. Okay, pressure exerted by an ideal gas. Can you guys just look at page 4 for the time being? Okay. All right, there's a derivation here that you will need to know. Okay. Pressure exerted by ideal gas. Just now it was mentioned to you that when you're talking about pressure exerted by a gas, it's actually due to the collision of the gas molecules against the walls of the container, right? So the gas molecules produces a force, exerts a force over the walls, and then you divide it over the area, you're gonna get pressure. Okay, so what you're interested to know is what is the equation for the pressure exerted. Okay, now this one in your syllabus, the derivation of this is required. You need to know how the equation is derived in addition to knowing the equation itself. Okay, there's a very lengthy derivation here covering the entire page. All right, so let's just start with some very simple principles. Okay, so as I mentioned, the overall pressure in any container containing a gas is actually produced by the collision of many gas molecules with the wall of the container. Okay, and each of these molecules actually move with different speeds in different directions. This is actually implying to you that they are in random motion. Remember just now one of the assumptions of the kinetic theory of ideal gases is that the molecules always move in random motion. So that would mean they would have different speeds in different directions. All right. So let's just analyze one simple gas molecule first. Consider a gas molecule with a mass of m in a containing vessel that is a cube with side of length L, traveling with a speed of cx in the x direction. Okay, so what you're seeing right over here in the diagram is actually your cube containing vessel. Okay, and it has a length of L. So each of the lengths, the width, the length, the height will all be length L. Okay, so this one will be L, this one will be L, this one by right should also be L. Okay, because it's a cube in the first place. Now you have a gas molecule, a single gas molecule that is moving horizontally. All right, let's just say that the speed is cx. Okay, so it moves horizontally. As it moves, it will eventually collide with this side of your wall. Okay, so when the molecule collides with the wall, it will actually rebound elastically with a velocity of negative cx. Remember just now in the previous page, one of the assumptions of the kinetic theory of gases, we also mentioned that the collisions of your molecules with the wall is supposed to be elastic. So when it's elastic, if right now your molecule hits the wall with a velocity of cx, it will by right rebound with the same velocity, just that it's in the opposite direction. So that you get negative cx here. Now, what we're interested to find out from here is the momentum change caused by the gas molecule itself. Our momentum change here, delta P, is actually mcx minus negative mcx, giving you 2 mcx. Okay, remember this little case here is very similar to something that you had done in AS physics when it came to learning about momentum. If I tell you that you have an object with mass m hitting with velocity v, and then rebounding with velocity v in the opposite direction, your change in momentum is going to be, let's just say you take the initial momentum minus final momentum, and that your rightwards is considered to be your positive sign convention, you will say it's mv minus negative mv. This one here will be positive p for you. This one here would be negative p when compared to your sign convention here. All right. So here you will get 2 mv. All right. So that time I mentioned you can take initial minus final or final minus initial, or you can even change your sign convention to be the opposite direction. Either way, you will always get back the same value of the magnitude. Okay. But you might get negative in some instances, but that's not really a concern. What you want is the magnitude. Okay. So this is what you learned in AS physics last time. You're doing exactly the same thing right over here. Okay, so your momentum change is just mcx minus negative mcx, giving you 2 mcx. All right, so get that one first. And then after that, what are the other things that you need to know? Now, the molecule will travel a distance of 2L before rebounding, before colliding again with the wall. Wait, let me just delete this little thing here. When your molecule hits the wall, when your molecule hit the wall just now, when your molecule hit the wall and then it rebounds, it will travel again to the other side of the wall, hit that wall, and then rebound back before hitting back the same wall again. Okay, now in your case, that molecule would actually travel a distance of 2L before colliding again with that wall, because you see, if you move from here to here, this one is L. And then if you move back from here to here, this one again is going to be L. So L plus L gives you 2L. All right. So why you want to use this is because you are trying to find out the time between collisions. Okay. Remember just now the assumptions of kinetic theory of gases, we mentioned that the time of collision is negligible compared to the time between collisions. Right now, you're actually trying to find the time between collisions, because that is the thing that you can actually measure. The collision time, the one that we were talking about here in 2 pages before this, the time of collision is negligible, it's very, very small. We cannot really measure it. So we instead use time between collisions. Okay, that's what we're trying to do. We want to measure the time between collisions right over here. So here, if we know that the molecule, if you want to find the time between collision, I actually already mentioned to you, is the time taken for the object to hit back the same wall after rebounding. So it's actually this red colored line here. So to find the time between collision, you need to also know the distance traveled. So you will use this equation from your kinematics last time. Remember that velocity is distance over time. So that time is actually distance over velocity. So you're trying to find out the time between collision, or rather the elapsed time t, you need to find out the total distance moved, which in your case is 2L, and your velocity that you're moving with, which in your case is cx. Okay, so this one here is actually time between collision. Okay, consider the time between collisions, not the time that the molecule is in contact with the wall. All right. Okay, so now that you know what is the momentum change right over here, and also the elapsed time, you can actually work out what is the force applied by the molecule on the wall. Because you know that force is equal to rate of change of momentum from again AS. Force is rate of change of momentum. You already found out change of momentum is 2mcx. The time is 2L over cx. You're going to get mcx squared over L. All right, so this one is one thing that you will do. This one is one thing that you will have. And then from there, you want to find pressure. This one here is force. You want to change it to pressure. So recall that recall that pressure is force per unit area. Wait. Pressure is force per unit area. So you take force divided by area, which in your case is mcx squared over L, which you already found here. And then what about your area? Your area is referring to this. Let me just erase this circle here. Your area that you're talking about is this area. And this one is actually 2L. Okay? Sorry, not 2L. L squared, because it's L times L. And this is your area. So pressure is force over area is mcx squared over L divided by L squared itself. You're eventually going to get mcx squared over L cubed. Now, L cubed will actually be your volume. So you get the equation as mcx squared over V. Okay, so this is one step. Now you go to another step. Now this pressure here that you have found is actually only for one molecule moving horizontally. This one is not representing the actual situation yet. Okay, because here it's only talking about one molecule moving horizontally hitting the wall. This is the pressure exerted by that one molecule. So you want to expand it further so that it actually covers all the gas molecules. Okay, so from here onwards, you're actually trying to expand your derivation to include the real life situation. Okay, so in your case, we know that your gas molecules would be a lot. It's not just one gas molecule. So you have a lot of gas molecules. Let's just call that the number of gas molecules that you have is N, capital N. Okay. If you have N number of gas molecules, the pressure exerted is going to be multiplied with N. So you get N mcx squared divided by V. You are actually just multiplying with N over here. Okay. And also, remember it was mentioned to you that when your molecules move, they are actually moving with all sorts of speed. They will be moving with different speeds. So because they're moving with different speeds, we tend to get the average speed. All right, so this is another improvement that we make to the derivation. Since molecules tend to move with different speeds, the average of speed squares is taken. All right, where you see right now, your cx square has this sharp bracket over here. Whenever you see a sharp bracket over a certain variable like this one, maybe I just write it at the top left hand corner. Whenever you see a sharp bracket over something, this one is actually talking to you about the mean or average value. Okay, so you see from here going on to here, the only thing that has changed is the cx square has now a sharp bracket over it. This means that you are actually using the average of the speed squared in the x direction. Okay, now when you have the cx square in sharp bracket, when you have the CX square and sharp bracket squared, that one is actually called a specific term. It's actually called mean square speed. Okay. It's called mean square speed. All right. Average of velocity square is called mean square speed. Now, sometimes you might be tempted to call it as something else. If you have this one is called mean square speed. Sometimes some people have a tendency to call it a different way. Sometimes they call it mean speed square. Okay. Is mean speed square the same as mean square speed? They are actually not the same. Okay, mean square speed is actually you taking the mean and then squaring it. Okay, they're different things. Okay, let me just highlight the differences to you here. All right, this one is not the same as this one. Okay, they are totally different and they are pronounced differently. Okay, the one that you're seeing in your equation here is called mean square speed. All right, don't ever say as mean speed square because it's referring to this. This one you need to know the term because your questions will ask you what is that symbol called. Okay, it's called mean square speed. All right, make sure you do not call it mean speed square. That is totally wrong. All right. Okay, now back to the derivation. Now, the improvements that you've made so far already took into account that you have many number of molecules and that your speed of the molecules can vary so that you are actually using the average value. Okay, but now you need to take into account the molecules that are moving in the other directions as well. Okay, all this while you only consider the molecules that are moving in the x direction. All right, in practice, your molecules don't only move in one direction, but actually three different directions in the x, y, and z axis directions. Meaning to say, if you look at your diagram right now, I could say to you that this one is your x direction, this one is your y direction, and then this one is your z direction. So your molecules could be moving in any three of these principal directions. Okay, now it's because of this that your molecules move in three different directions. You can actually say that mean square speed is equals to mean square speed in the x direction plus mean square speed in the y direction plus mean square speed in the z direction. You can think of this as something like the resultant. Okay, now how can I say this? It's because of something like this now. I mean, this one has something to do with your understanding of geometry. If I give you y and then I give you x, the resultant of what x and y would be this one, right? This is your resultant, isn't it? Then after that, if this one is your resultant, and then I tell you you have z in this direction right now, the new resultant will be something like this. This is your new resultant. Okay, it's a bit hard to visualize, okay, unless I try to draw in 3D. The idea is this one, because you see, if I have something moving in the x and y direction, I know that vector x plus vector y would give me this one. This is my new resultant. Okay, so that resultant is somewhere like this. Okay, which is actually perpendicular to your z. So if your resultant is like this, and then you have z, which is also perpendicular, you can actually again say that z plus your resultant gives you your new resultant. Okay, so the idea here is that this resultant here is square root of x squared plus y squared. All right, because it's a right angle. Then after that, this resultant is over here, x squared plus y squared. You're trying to add up with z. Your new resultant would actually be z squared plus your resultant square, which in turn will become z squared plus x squared plus y squared. That's how you can get something like this right over here. Okay, your mean square speed, that one right over here, is actually something like your resultant. Okay, it is actually formed by your x, y, and z velocities combined together. Okay, how they got this was by you trying to analyze them in 3D. That's how you got this expression. Okay, but in your current case for A level, you actually don't really need to know so much about how this one came about. All you just need to know is that because when you try to take into account that the molecules move in 3 different directions, the conclusion is that the resultant mean square speed would be the sum of the mean square speed in the x, y, and z directions. That is the only conclusion that you need to do from here. Okay, so just take it as it is now. All right, you don't need to worry about how do you get that. All right, okay, so this one you will get this resultant mean square speed is the same as the sum of mean square speed in the x plus y plus z plus the z direction. Okay, this is one thing you have. Okay, one last thing is the part where we tell you because the molecules are moving randomly, therefore c square is equals to cx square equals to cy square equals to cz square. Okay, what does this one mean? It kind of means something like this lah. Equal proportions of molecules moving in x, y, and z direction. Okay, because they move randomly, it's random, you expect that there are equal proportions of molecules moving in the x direction, equal proportions of them moving in the y direction, equal proportions of them moving in the z directions, so their average would be the same in the x and y and z direction. And because they're the same, your mean is also the same as your mean square speed. Okay, so taking into account these two information, your equation can be simplified to c squared is equals to cx squared plus cx squared plus cx squared, giving you 3cx squared. And then from there, cx squared is actually 1/3 of c squared. Your mean square speed in one direction, which is x direction right now, is actually 1/3 of your resultant mean square speed. Okay, so your resulting equation would be this one. Okay, P1 over 3 nm c squared over v. Okay, you see it's this one, right? So if I go and sub in for this one, you're going to get P is equals to nm over v 1 over 3 mean square speed, thus giving you P is 1 over 3 nm c squared over v, which you can then shift the v around to here, giving you PV equals to 1 over 3 nm c squared. Okay, this is the equation that you need to remember when it comes to the pressure exerted by an ideal gas inside a container. Okay, and the derivation is something that you need to know. Okay, I think most of the time is usually this part here where people start to get confused. All right, but I think from the beginning all the way to here, this one is good. Everyone can understand that. It's just this portion here that people start to get a bit confused. All right, So there's a detailed analysis for it, all right? But I won't go into the detailed analysis. I'm just going to tell you the simplified version of it, the simplified conclusion of it, okay? So all you just need to know is that because your molecules move in 3 different directions, we tend to say that Cx squared is equals to Cx squared plus Cy squared plus Cz squared. But because the molecules move randomly, we expect equal proportions of them moving in all the different directions. So we can say Cx squared is equals to Cy squared equals to Cz squared equals to C squared. Then after that, we get this. All right. So yeah, it will take some time getting used to, all right? But don't worry about it. The past years don't usually ask this as much. They do ask, but not that often. And even if they do, it's actually a very simplified version of what you're seeing right over here. Okay, but you still need to know how it's derived, just in case. All right. Okay, so your equation is PV equals to 1 over 3 NMC squared. You can actually modify this equation a little to become this. Okay. Now, how did it become PV equals to 1 over 3 NMC squared to PV equals to 1 over 3 rho C squared? Now, if you recall a few things, N was number of gas molecules. M is mass of one gas molecule. Okay. Now, in the chapter of ideal gas, this is where you need to be careful a little because a lot of times people always assume that M is the mass of the entire gas. That's not true. The M here is actually referring to the mass of one gas molecule itself. All right, so just be careful about that. Now, if you have N is number of gas molecules and then small m is number or mass of one gas molecule, what then is Nm? Nm is actually the mass of your gas, includes all the gas molecules. Okay, Nm is your actual mass of your gas. It includes all your gas. It includes all your gas molecules. All right. So now what you want to see is this. If you look at the equation that you have right over here, if this one is mass of gas, and then this one is volume, isn't this going to give you density? This one here is actually the density of your gas. All right. So that same equation can be modified to become this. It's just a simple interpretation, finding what is the expression for density. Okay, so these two you need to know. Any equation that you see in this chapter that is in a yellow color square box, these are required to be known. Okay, you need to know these equations before you are able to do some of the questions. All right. Okay, so you have the equation for pressure exerted by ideal gas inside a containing vessel. Now it's from here that you can actually derive something else from that equation. You can actually use the equation that you just derived to further derive another different equation, which is the average kinetic energy of molecules, specifically the average kinetic energy of your gas molecules. Okay, it can actually be shown that the average kinetic energy of gas molecules is directly proportional to absolute temperature. All right. Now you have learned two equations so far. The PV equals to 1 over 3 NMC squared is something that you just derived. The PV equals to NKT is another separate equation that you derive on the first page. Notice that these two have the same expression on the left side. Both are PV. If you equate both of them together, you're going to get 1 over 3 NMC squared equals to NKT. So you go and cancel off N, you're going to get MC squared equals to 3KT. Now from here, you want to do something else to it. Let's just say you go and multiply by half. If you have MC squared equals to 3KT, you multiply both sides by half, you're going to get half MC squared equals to 3 over 2KT, isn't it? You're going to get this. Now, this equation here is actually similar to the Ke equation of half mv squared, isn't it? So here you see m is your mass of gas molecule, c is your mean square speed, okay, is your mean square speed. This one is actually your average kinetic energy of your gas molecule. Okay, so that's why I can say that average kinetic energy of gas molecule is actually the same as 3 kT. And then K is constant here, is your Boltzmann constant. K is constant, therefore EK is proportional to T. That's why you can say this. Average Ke of gas molecules is directly proportional to absolute temperature. All right. Okay, there's something here that you would need to know. The EK or half mc squared here is the average kinetic energy of a single molecule only. Okay, the value is for one molecule only. Okay, what do I mean by that? It will be easier if I give you the example for masses. Let's just say if I tell you you have 5 people inside a room. Okay, you have 5 people inside a room. 1, 2, 3, 4, 5. And then you all have different masses. This guy is 60 kg. This guy is 85 kg. This guy is maybe 72 kg. And then this one maybe 68 kg. And then this one 73 kg. So if I ask you what's the average mass of this 5 person, you will say, oh, it's 60 plus 85 plus 72 plus 68 plus 73 divided by 5, right? So 60 plus 81 plus 72 plus 70 plus 73 divided by 5, you're going to get the mass as 71.6 kg for the average mass. So this value, average value of mass, is correct to say is actually for one person, isn't it? You're actually saying that, oh, for this group of 5 people inside the room right now, their average mass is this one. That one person on average will be having this mass. Okay, so it's a similar concept here. When you're talking about this little thing, this little expression here for the kinetic energy, it is the average kinetic energy of a single molecule only. It is representative of one molecule only. Okay, so just remember that. Now, from here, you need to expand it a little. If this EK or half mc squared is the average kinetic energy of one gas molecule only, what if you want to find the total kinetic energy of all the gas molecules? So if you want to find the total kinetic energy of all the gas molecules, all you just need to do is you take the number of gas molecules multiply with the average kinetic energy of one gas molecule. And since this one was equals to 3 over 2 kT, your expression now becomes Ke total equals to 3 over 2 nkt. Okay, the only difference now you see is that you are multiplying with n. When you multiply with n, you're getting for the whole gas. Okay, total kinetic energy representing total energy of all molecules. This is actually talking to you about the whole gas. All right. Same like this concept here. If I ask you what is the total mass, you will tell me it's actually 5 times 71.6 to give you the values of the total mass. Isn't it? Similar case here. All right. Okay, now from here, you will start to relate a little with what you learned from thermal properties. Remember, I mentioned to you before that ideal gas by right has no molecular potential energy. So its internal energy is actually just the molecular Ke of its gas molecules. Just to recap for you, IE is Ke plus Pe. So if your Pe is gone, therefore IE is just Ke. No? That is for this one. All right. So if IE is just the KE, that would mean that IE, internal energy, is 3/2 NKT. Okay, that's why I can say this also. Internal energy of your gas molecules is actually 3/2 NKT. Because this one is talking about the kinetic energy only, which I already found out from the previous part of the notes. Okay, right? Okay, this one is the last complicated thing that you need to remember. The rest of everything from here on out should be quite simple. Okay, now mean square speed is not the same as mean speed squared. This one I explained already just now in the previous part of the notes. Mean square speed is not the same as mean speed squared. Just be very careful about the terms that you're using, all right? And then after that, the mean square speed, because it's a square, you can actually root it, square root it. So when you square root your mean square speed, you get something called root mean square speed, which is called CRMS, square root of mean square speed. Okay, this one is called root mean square speed, RMS. Okay, right, you will sometimes be asked to find the root mean square speed in your questions. You just square root your mean square speed. All right. Okay, to summarize, you generally have all these equations here that you need to remember. And there are certain situations where you will use those equations. It depends on what the question asks, right? Now, for specific questions that ask you about the root mean square speed or mean square speed, you generally use these two equations that you've just seen, all right? But for questions that involve finding the number of molecules here being n, you will generally use PV equals to NKT, all right? But for questions that involve you finding number of moles, which is your small n, you again use PV equals to nRT, all right? Then after that, when the question asks you something and it doesn't fit any of the four cases here, you generally use this P1 V1 over T1 is P2 V2 over T2. Okay, but this one you can only use when the number of moles of the gas is the same on both sides. Meaning to say before and after you did not add anything to the gas, you did not remove anything from the gas. Okay, but this one is not really used frequently. Okay, this one is very infrequent, very seldom. It's very seldom you will use in your past year. It's the first four that you will use a lot. Okay, right? So this is the complicated part of ideal gas all dusted off. Yeah, it takes quite a bit of time to digest because you notice that there is a lot of equations here and there, and there seems to be 3 different derivations to learn. Yeah, it's like that one. Okay, ideal gas is short, but it seems to be complicated in the sense that it has quite a lot of derivations involved, and the derivations are a bit complicated because they have a lot of little variables here and there. All right, but eventually you get used to it. Right, so let's just do some questions. We can do some simple ones. Next week will be the somewhat more difficult ones. Today is just the concept. All right, have a look at ideal gas worksheet. You can have a look at page 1 actually. Let me just open up. Okay, ideal gas worksheet. Just have a look at the ideal gas worksheet and then have a look at page 1. This is the first page. Okay, this is June 15 P42. So let me just see the question 2. All right, now in a sample, in a sample of gas at room temperature, 5 atoms have the following speeds. Okay. In a sample of gas at room temperature, 5 atoms have this following speed here. For these 5 atoms, calculate to 3SF, 3 significant figures is already stated here. Calculate out the mean speed and the mean square speed. Okay. Now mean speed, I think this one quite easy. You can actually do it relatively easy. Mean speed is just you adding up all the speeds and then divided by the number of molecules, number of atoms. In other words, mean speed is C1 plus C2 plus C3 plus C4 plus C5 divided by the number. So this is what you're going to get. The final answer will be 1.44 times 10 power 3. Okay. Because they all share the same factor, you can actually factorize them out and then just add up the insides. Okay. Then you get your answer as 1.44 times 10 power 3. So far, this one should be okay. Okay, then you move on to the next one. The next part of the question asks you to find out the mean square speed. Okay. Mean square speed is referring to this one. Okay. Mean square speed would be you squaring all the speeds and then finding the average. This one, what you will need to do is you square all the speeds before averaging, which is actually what you're doing here. C1 square plus C2 square, C3 plus C3 square plus C4 square plus C5 square, then divided by the number. Okay, so same thing. You have a common factor here. You factorize it out, but don't forget to square this one. And then after that, the inside, you start adding them up, but square each one of them before dividing by 5. Then your answer will be 2.09 times 10 power 6 meter square per second square. Okay. Okay. Right. So this one should be okay. All right. So this is how you find mean square speed. Yeah, a common mistake that most people have done for this paper is that they go and find the mean and then they square. Actually, you can do your comparison here. You see, you can actually prove that mean square speed is not the same as mean speed square. Your mean speed square, so mean square speed here is 2.09 times 10 power 6. If you want to get your mean speed square, you already find the mean speed. If you take 1.44 times 10 power 3 and you square, you will notice that your answer is not going to be the same. It's nowhere the same. Okay, 1.44 times 10 power 3, square the answer, you're gonna get 2.07 times 10 power 6. Okay, not the same. Okay, this one is 2.09, this one is 2.07. All right, so they're not the same. All right, just be careful about that. Okay, the last part is just asking you to find out the root mean square speed. Root mean square speed, the RMS speed. You just take whatever speed you have here for the mean square speed, you square root it. All right, so root mean square speed is the mean square speed square rooted. You get 2.09 times 10 power 6 square root of it. You're going to get 1.45 times 10 power 3. And this is your answer. Okay, so far so good. This is your answer. Okay, so this one is okay. Then after that, we can actually move on to something else a bit more challenging. Page 5 of your ideal guess worksheet. Wait, let me just see that. Okay, you can actually now look at page 5 of your worksheet. This is March 16 P42. 16P42. Number 2 is actually one of the questions that we just did. All right. What is meant by internal energy? This one, I think we actually kind of went through this already just now. Internal energy is the sum of a random distribution of kinetic and potential energy of molecules inside a system. You can actually copy out the definition from your notes. Okay. The ones that is written here, as I mentioned, is a bit different from what is inside the notes, but they're actually talking about the same thing. All right. So my suggestion to you will be just to copy from the notes now, all right, in order to make your definitions more consistent. Now, part 2, the basic assumption of the kinetic theory of gases that leads to the conclusion that there is zero potential energy between the molecules of an ideal gas, right? They're asking you to state what is the assumption of kinetic theory of gases that led you to conclude that there's no potential energy between molecules. What tells you that there's zero molecular potential energy? This one I've mentioned before is mainly due to the fact that your molecules do not have forces between them. There are no forces between the molecules, or you can just simply say there are no intermolecular forces. This one is pretty straightforward. Okay, this one is all right. Okay, so if this one is okay, then we move on to the other part, part B. Now, pressure P and volume V of an ideal gas are related by this equation. PV is equal to NM, PV equals to 1 over 3 NMC squared, where N is the number of molecules, M is the mass of a molecule, and C squared is the mean square speed. Use the equation to show that the mean kinetic energy of a molecule is given by this. How do you show that the mean kinetic energy of a molecule is given by this? We actually did the derivation before 10 minutes before this. Okay, so we can actually do this. All right, show that from this equation, show that you can get this. You actually need to use PV equals to NKT. This added with this, or rather combined with this, will give you this. So you need to show the derivation. So PV is equals to 1 over 3 NMC squared, the first equation. PV is equals to NKT, second equation. Equate both of them, you're going to get 1 over 3 NMC squared equals to NKT. N will cancel off, giving you MC squared equals to 3KT. You want to change it into a form that is equal to a KE. You want to change it into a form equivalent to KE. So this one you multiply by half. You're going to get half MC squared equals to 3 over 2 KT. Okay. Now, from there, you actually need to go and write this statement. Since EK is equals to 1/2 MC squared, therefore, EK equals to 3 over 2 KT. Okay. If you stop right over here, this one won't get you the full marks. Okay, if you stop right over here, you won't get the full mark. You have to specifically mention that half MC squared is actually EK. Therefore, EK is actually 3 over 2 KT. Okay. So derivation is done. It's actually following what you saw in the notes. This one is for 3 marks. Okay, now then after that you move on to the next page. Okay, this one is more like what I've just done for you in the last page. I mean the last page of the notes just now. Okay, let's read the question. You have a cylinder that contains 17 grams of oxygen at the temperature of 12 degrees centigrade or Celsius, whichever you want. The mass of 1 mole of oxygen gas is 32 grams. It may be assumed that oxygen gas behaves as an ideal gas. Keyword found. It is behaving like ideal gas. For this oxygen gas in the cylinder, what is the mean kinetic energy of a molecule? Okay. keyword, what is the Ke of a molecule? So this one, you can actually just make use of what you just done. You know that Ek is 3 over 2 Kt, because here, just now you found this, right? Half mc squared is 3 over 2 Kt, where this one is Ek, right? You don't have the mean square speed. That's why you cannot use this straight. But you have the other one, which is 3 over 2 Kt. That's why you're just using 3 over 2 Kt straight. Okay? You don't use half mc squared here because you do not know the c squared value. But you know the value of the temperature and the value of the Boltzmann constant. So you use 3 over 2 Kt. Okay? So 3 over 2, Boltzmann constant is 1.38 times 10 power minus 23. This one you can actually get it from the second page of your notes. Sorry, not second page of your data sheet actually. Second page of your exam paper is usually listed there. This is your value of your Boltzmann constant. 1.38 times 10 power minus 23. Okay. You can also get the values from the notes now. It's a shortcut. All right. So your value of K is this. The other thing you need to be careful about, as I mentioned, T must be in Kelvin. So if your case here is 12 degrees centigrade, you need to change to Kelvin, which means that you need to plus 273.15 Kelvin. Okay, that's why you see is plus 273.15. Now, I mentioned this to you guys before. If you just want to plus 273, it's perfectly fine. If you want to plus 273.15, it's also fine because there's two different contradicting answers. I mean, both are acceptable. Let me just show it to you. Hey, wait. Let me just show it to you why is there 273.15. Okay. In your syllabus booklet, you're required to know how to convert between Kelvin and degrees Celsius and recall that temperature in Kelvin is temperature in degrees centigrade plus 273.15. Okay, so this one is, they've already told you you can use 273.15. The syllabus booklet itself say you can use. Okay. If you're talking about the marking scheme itself put it as 273. Let me just open it up for you. March 2016 P42. I'm not sure whether it's listed, but I think it should be. March 2016 P42 question 2. Yeah, it's also written there. You see, in your marking scheme, when it came to converting your temperatures to Kelvin, they just use 273. Okay. Marking scheme tends to put it as 273. Syllabus booklet tends to put it as 273.15. Either way is fine, all right? So if you feel that the 0.15 is kind of like a hassle to put, you don't really need to put it in. But I have a tendency to put it as 0.15, all right? Just so you know. So eventually your kinetic energy would be 5.9 times 10 power minus 21 joules. This is the kinetic energy of a molecule. All right. So far, so good. Now, the next one they'll ask you is, what is the number of molecules? Now, to find number of molecules, you can have actually just used this. Number of moles is number of molecules divided by your Avogadro constant. Okay. So that number of molecules is number of moles times your Avogadro constant. You need to find out what is your number of moles right now for your oxygen gas. You can actually do it from the information given. You see, they told you that 1 mole is 30. Okay, wait, let me just rewrite it in a different manner. They told you that 32 grams is 1 mole. How much is 17 grams then? If I want to find out the number of moles. This one you will actually use something like ratio. 17/32 times 1 gives you your number of moles, which is what you're doing right over here. And this is finding out the number of moles. Then you multiply with your Avogadro constant, giving you your final answer as 3.2 times 10 power 23. Okay, so far so good. All right. Okay, then the next one would be find out the total internal energy. Okay, keyword is internal energy. All right. So another keyword just now I mentioned to you is ideal gas, right? So IE is KE plus PE for ideal gas, no intermolecular force. For ideal gas, no IMF, PE, sorry. For ideal gas, no intermolecular force, therefore PE is 0. IE is just your KE. Okay, your KE here is for the whole gas, for all gas molecules. So I mentioned to you, if you want to find the KE of the whole gas that includes all the gas molecules, you need to take n times your average kinetic energy of one gas molecule, which you already found in part 1 and 2. You already found N and EK in part 1 and 2. So all you just need to do is to multiply them together. Okay. So your internal energy is N times EK. Just multiply their values together. You're going to get 1.89 times 10 power 3 joules. Just like that. Okay. Right. So this one, page 5 is done. Then we can move on to page 13. Let me see whether page 13 is a complicated example. Okay, we can then now move on to page 13. Okay, now page 13 is something to do again with your thermal properties. This one is a good question to do, although we only have 5 minutes left. Okay, right. Have a look at page 13. This is another question we can do. March 2018 P42. Okay, for this particular question, you have a cylinder that contains 5.12 moles of an ideal gas at a pressure of 5.6 times 10 power 5 Pascal and a volume of 3.8 times 10 power 4 centimeter cube. Find out the temperature of the gas. This one is pretty straightforward. You can just use straight away PV equals to NAT because they already give you number of moles. All right. So sum in your values. 5.6 times 10 power 5, 3.8 times 10 power 4 times 10 power minus 6. Where did the 10 power minus 6 come from? It's because you see you have a centimeter cube. So 1 centimeter cube is the same as 1 centimeter cube, the entire thing. 1 centimeter is 10 power minus 2 meter cube everything. You're going to get 10 power minus 6 meter cube. That's where this 10 power minus 6 came from. You're changing it to meter cube. Okay. Then number of moles 5.12, molar gas constant is 8.31. Find out what is your T. T is 500 Kelvin. Just like that. Okay. This one is worth 2 marks. Okay, then after that we look at part B. Okay, let's have a look at part B. Let me erase this. Now, in part B, they mentioned to you that the average kinetic energy of a molecule of the gas is given by this expression, where K is the Boltzmann constant and T is the thermodynamic temperature. Thermodynamic temperature is already your temperature in Kelvin. Okay. The gas is heated at constant pressure, so that its temperature rises by 125 Kelvin. Use your answer in A to determine the new volume of the gas. Okay. Use the answer that you just found to find out the new volume of the gas. All right, now you are basically changing your gas from state 1 to state 2. All right, so under both cases, the equation PV equals to nRT would apply to both cases. All right, so you're trying to use something like a ratio method again to compare both. But usually before you can do that, you need to identify what is constant for both of them, right? So if I start off with PV equals to nRT, I know that pressure is constant because the question is it here. So P is constant. And then I know that the gas was not removed, neither was it added during the process from state 1 to state 2. So number of moles remains the same, okay? Because it didn't add or remove anything from the gas. And needless to say, molar gas constant is also a constant. So P, N, and R are constant. Therefore, V is proportional to T. V2 to V1 is equals to T2 to T1. So you want to find the new volume, which is V2. Okay. So V2 is T2 over T1 times V1. T2 is actually going to be 500 times 125, 500 plus 125 divided by 500. Okay, because here your question mentioned this. Your temperature rises by 125. It was added, it increased by 125. 125 is not the temperature itself. It's telling you the increase. Okay, that's why you need to add 125. Okay, T2 is 500 plus 125 divided by 500, multiply with your volume. 3.8 times 10 power 4. So eventually you're going to get the answer as 4.75 times 10 power 4 centimeter cube. All right, so this is your answer.